Welcome! In this session, we'll be exploring an interesting problem titled Low-Quality Data Detected. Together, we'll break down the problem, analyze potential approaches, and understand the thought process required to solve it effectively. Let's dive in. To begin, let's consider the brute force approach. This method involves iterating through the entire dataset and checking each data point individually to determine whether it meets the criteria for good quality or should be flagged as low quality. The intuition here is straightforward: systematically inspect every data point without relying on pre-processing or extra structures. This ensures that no data point is missed, making it a simple and comprehensive approach. However, it comes with trade-offs. While the implementation is easy and requires minimal space, just a few variables, the time complexity of O(n) means it doesn't scale well for very large datasets. For example, if the dataset contains millions of entries, the linear scan can lead to significant performance bottlenecks. Now, shifting to a more efficient method, the optimized approach introduces pre-processing to reduce redundant checks. By calculating summary statistics or leveraging auxiliary structures like hash maps, we can streamline the validation process. For instance, thresholds or patterns defining low-quality data can be pre-computed, allowing us to narrow down potential issues quickly. If there are anomalies or duplicates to detect, techniques like sliding windows or binary search can further optimize the process. This approach involves an upfront cost for pre-processing, but the payoff is substantial when dealing with large datasets, as repetitive calculations are avoided. With a time complexity of O(n) for pre-processing and O(k) for validation, where k is the number of low-quality data points, and a space complexity dependent on the size of auxiliary structures, this method is both scalable and efficient for repeated validations. An alternative approach involves leveraging machine learning for scenarios where the definition of low-quality data is unclear or highly context-specific. Here, we can train a model, such as a decision tree, logistic regression, or even a neural network, to classify data points based on labeled examples. The key advantage of this method is its ability to handle complex and nuanced patterns that may be difficult to define with hard-coded rules. For instance, a model can learn from historical data to identify subtle indicators of low quality. The time complexity for training the model is typically O(n), while inference for each data point can be as fast as O(1). However, this approach has its trade-offs. It requires labeled training data, which may not always be available, and computational resources for both training and deploying the model. Additionally, the space complexity depends on the model size and the features included during training. While this method is powerful for complex problems, it might be unnecessary for simpler cases where threshold-based criteria suffice. Overall, machine learning is a highly effective tool for ambiguous or dynamic definitions of low-quality data but can introduce overhead in terms of setup and resource requirements. The strategy we chose to implement is the optimized approach because it strikes the ideal balance between efficiency and simplicity. By incorporating a pre-processing phase, we can handle large datasets with repeated checks in a highly efficient manner, while keeping the main validation phase straightforward to implement. This approach avoids the scalability issues of brute force and the overhead and complexity associated with machine learning. The pivotal insight here was recognizing that pre-processing metrics or utilizing auxiliary data structures, such as hash maps, can significantly minimize redundant computations. For example, detecting duplicates as low-quality data becomes much faster when a hash set is used, allowing us to identify duplicates in O(1) time after an O(n) pre-processing setup. The brute force method, though conceptually simple, was deemed impractical for large-scale datasets due to its linear nature and performance limitations. Machine learning, although powerful, was unnecessary for this problem's relatively straightforward requirements. The optimized approach, on the other hand, offers a scalable and robust solution that is well-suited for real-world applications. While there is an upfront cost for pre-processing, the gains in runtime efficiency far outweigh this cost, making the approach both practical and effective for handling large datasets. To begin, the algorithm starts with input parsing. This involves reading the dataset into memory and ensuring it is clean and structured for further analysis. Depending on the problem, the dataset can be in various formats, such as a list, array, or any data structure that suits the requirements. For example, if the dataset is a list of integers, we need to check for and remove any null values or invalid entries to ensure the data is ready for processing. Next, we iterate over the dataset using a simple loop. Let's represent the dataset as an array called data with size n. The loop will traverse through all indices, from I equals 0 to n1. During this traversal, the algorithm applies a quality check to each data point. For every element data, I, a validation condition is used to determine whether the data point meets the quality criteria. This condition can vary based on the problem requirements. For instance, if the criterion is that a data point must be greater than 10, the algorithm would check if data, I, 10 for each element in the dataset. Now, when a data point fails the quality check, the algorithm flags it as low quality. This can be achieved by appending the index or the value of the failing element to a separate list, which we can call low_quality. For example, if an element at index I does not meet the quality condition, we add either I or data, I, to the low_quality list. Once the entire dataset has been processed, the algorithm outputs the results. These results typically include the list of flagged low-quality data points or a summary of the validation outcomes, such as a count of how many points failed the checks. For instance, the algorithm might print the low_quality list or state something like, 3 elements failed the quality criteria. Additionally, it is essential to handle edge cases to ensure robustness. Scenarios such as an empty dataset, all elements passing the quality check, or all elements failing it must be accounted for. For example, if the dataset is empty, the algorithm might return a message like no data points to validate. Similarly, if no elements are flagged as low quality, it would return all data points are good quality. This ensures that the algorithm behaves predictably under all circumstances. This algorithm relies on an iterative approach, utilizing a loop to methodically traverse the dataset and validate each data point. While the complexity is O(n), this approach is efficient and ensures every element is accounted for, especially when dealing with small to medium-sized datasets. A key strength of this method lies in its modular validation function. Since the quality check is encapsulated in a separate function or condition, it can be easily customized for various definitions of good quality. This flexibility allows the algorithm to adapt to a wide range of problems. Robustness is another critical aspect, achieved through the explicit handling of edge cases like empty datasets or extreme values. By addressing these uncommon scenarios, the algorithm avoids failure in edge conditions. For the data structures, the dataset is stored in a list or array due to their efficient indexing and traversal. The low-quality data points are stored in a separate list, which is simple to manage and easy to query when generating the final results. The most computationally intensive operation in this algorithm is the validation step, as it is performed for every data point in the dataset. Optimizing the validation logic, such as minimizing redundant calculations, can significantly improve performance. The storage operation, specifically appending elements to the low_quality list, is very efficient with a time complexity of O(1), ensuring minimal overhead during the iteration process. Summarizing the results at the end is straightforward since the low_quality list already contains the necessary information. To further enhance efficiency, certain optimizations can be applied. For instance, if the dataset is sorted or structured in a way that allows early termination of the loop, such as using binary search for threshold checks, the algorithm's complexity can be reduced. For very large datasets, parallel processing is another optimization strategy. By dividing the dataset into chunks and validating them simultaneously across multiple threads or processors, the overall runtime can be significantly decreased. Let's walk through an example to see the algorithm in action. Consider the dataset data equals 12, 7, 15, 5, 20, and the validation criterion data, I, 10. First, the algorithm reads the dataset 12, 7, 15, 5, 20. It then begins iterating through each data point. At index 0, the value 12 satisfies the condition, so no action is needed. At index 1, the value 7 fails the condition, so 7 is added to the low_quality list. Similarly, at index 2, the value 15 meets the condition, while at index 3, the value 5 fails and is added to low_quality. Lastly, at index 4, the value 20 satisfies the condition. After completing the iteration, the low_quality list contains 7, 5. The algorithm then outputs the results, summarizing that 2 low-quality points were found. This example demonstrates how the algorithm processes each data point systematically and produces clear, actionable results. This code solves the problem of identifying which sensor is faulty when discrepancies arise between two sensors' readings. The bad sensor method takes two lists, sensor 1 and sensor 2, representing the readings from two sensors. The goal is to determine if one of them is faulty, and if so, which one. The function first determines the length of the readings. It then iterates through the lists to locate the first mismatch between sensor 1 and sensor 2. Once a mismatch is found, the code checks two conditions. 1. Whether the remaining readings of sensor 1 match the readings of sensor 2 after skipping the mismatched index. If this condition is true, sensor 1 is deemed faulty, and the function returns 1. 2. Similarly, it checks if the remaining readings of sensor 2 match those of sensor 1 after skipping the mismatched index. If so, sensor 2 is faulty, and the function returns 2. If neither of the above conditions is satisfied, it means the data inconsistency cannot be attributed to either sensor, and the function returns -1. If no mismatches are found during the iteration, the function concludes that neither sensor is faulty and also returns -1. This solution is efficient, as it traverses the lists at most twice, resulting in a time complexity of O(n). The use of slicing ensures clarity when comparing segments of the lists, and the overall structure is clean and easy to follow. Here, we begin by defining our solution within a class named solution. The method badSensor takes two integer arrays, sensor 1 and sensor 2, which represent the data readings from two sensors. The first step is to determine the length of these arrays, stored in the variable n. Next, we iterate through both arrays simultaneously using a for loop that stops before the last element. The goal here is to locate the first mismatch between the two sensors' data. Once a mismatch is found, we check whether sensor 1 could be the faulty sensor. To do this, we loop through the remaining elements from the point of mismatch in sensor 1 and compare them with the corresponding shifted elements in sensor 2. If at any point the values do not align, we set is sensor 1 faulty to false and stop further checks for sensor 1. However, if sensor 1 consistently matches the shifted data from sensor 2, we conclude that sensor 1 is indeed faulty and return 1 to indicate that result. If sensor 1 isn't determined to be faulty, we then proceed to check if sensor 2 has the issue. Similar to the previous check, we loop from the mismatch index and compare the remaining elements of sensor 2 with the corresponding shifted elements in sensor 1. If at any point the values do not match, we set is sensor 2 faulty to false. However, if sensor 2 consistently matches the shifted data from sensor 1, we return 2, indicating that sensor 2 is faulty. If neither array satisfies the conditions for being the faulty sensor, we return -1 to indicate that the fault cannot be determined. Finally, if no mismatches are found in the entire iteration, we also return -1, as this implies that the data in both arrays are consistent and no fault is present. Here, we start with the first example where sensor 1 is 1, 2, 3, 4, and sensor 2 is 1, 2, 4, 4. The length of the arrays is initialized as n equals 4. The algorithm begins by iterating through both arrays to find the first mismatch. At index 0, the values are both 1, so there's no mismatch. Similarly, at index 1, both values are 2, so we continue. At index 2, sensor 1 has 3 while sensor 2 has 4, which is the first mismatch. Next, we check if sensor 1 is faulty by comparing slices. The slice sensor 1, 2 is 3, 4, and comparing it to sensor 2, 3, which is 4, shows they are not equal. This means sensor 1 is not faulty. Then, we check if sensor 2 is faulty by comparing sensor 2, 2, which is 4, 4, to sensor 1, 3, which is 4. As these are equal, we determine that sensor 2 is faulty. Finally, for this example, the algorithm concludes that sensor 2 is faulty and returns 2. Moving on to the second example, sensor 1 is 1, 2, 3, 4, 5, and sensor 2 is 1, 2, 3, 5, 5, with n equals 5. The iteration begins to detect mismatches. At index 0, both values are 1. At index 1, both are 2. At index 2, both are 3. However, at index 3, sensor 1 has 4 while sensor 2 has 5, and this is identified as the first mismatch. To check if sensor 1 is faulty, we compare the slice sensor 1, 3, which is 4, 5, with sensor 2, 4, which is 5. Since these are not equal, sensor 1 is not faulty. Then, we check if sensor 2 is faulty by comparing sensor 2, 3, which is 5, 5, with sensor 1, 4, which is 5. These slices are equal, indicating that sensor 2 is faulty. Therefore, the algorithm returns 2 in this case as well. In the third example, both sensor 1 and sensor 2 are 1, 1, 1, with n equals 3. The algorithm starts iterating through the arrays. At index 0, the values are both 1. At index 1, the values are again both 1. At index 2, the values are still both 1. Since no mismatches are found throughout the arrays, the algorithm concludes that no faults exist. In this case, the result is -1 to indicate the absence of any discrepancies between the sensors. The key takeaway from this approach is the systematic way mismatches are identified and analyzed. The algorithm iterates through the arrays to find the first index I where the values differ. If the slice sensor 1, I matches sensor 2, I plus 1, it indicates that sensor 1 is faulty. Conversely, if sensor 2, I matches sensor 1, I plus 1, it suggests that sensor 2 is faulty. If neither condition holds or no mismatch is found, the algorithm returns -1, signifying that no faults were detected. This logic ensures that the solution is both efficient and robust for identifying the faulty sensor in various scenarios. To analyze the time complexity of the bad sensor function, let's break it down step by step. The function processes two lists, sensor 1 and sensor 2, of length n. The key operation here is the for loop, which iterates from I equals 0 to I equals n2. In the worst case, this means the loop runs n1 times. For each iteration, the function first checks if sensor 1, I, is not equal to sensor 2, I. This condition check is a simple comparison and takes constant time, or O1. However, if a mismatch is detected, two slice comparisons are performed to verify the fault. Slicing creates a new sublist from index I to the end, which has a size of ni. Comparing two lists of size m takes m time. So in the worst case, when the mismatch happens at the beginning of the lists, the slices would be as large as n, making the slice comparisons take n time. These operations form the basis of the time complexity for this function. When we consider early returns, the runtime of the function becomes dependent on where the first mismatch occurs. In the best-case scenario, there are no mismatches, so the loop simply runs its n1 iterations, performing only the constant time O1 comparisons. This gives a total time complexity of O(n). For the average case, if a mismatch occurs at some intermediate position I, the loop runs 4 I iterations, and the slice comparisons take time proportional to the remaining elements, O(n)i). On average, this still results in a complexity of approximately O(n). In the worst case, a mismatch occurs at the very first index. Here, the loop performs one iteration, but the slice comparisons dominate the computation time, each taking O(n). As a result, the total worst-case time complexity remains O(n). This analysis highlights how the function efficiently handles mismatches while maintaining linear time complexity in all scenarios. Now, to mathematically prove the overall time complexity, it's clear that the dominant operation is the slice comparison, which can take up to O(n) time in the worst case. The O(1) comparison inside the loop is negligible in comparison to the slicing costs. Therefore, the overall time complexity of the bad sensor function is determined to be O(n). Shifting focus to space complexity, the memory usage depends on the input and the operations performed. The input lists sensor 1 and sensor 2 require O(n) space each, as they are directly passed into the function. Additionally, during slice comparisons, new sublists are created. The size of these sublists depends on the index I. In the worst case, where slicing starts from I equals 0, the size of the sublists can reach up to O(n). This additional memory usage from slicing is a key factor in the space complexity. In addition to the slicing, the function uses a small, constant amount of auxiliary space for variables like n and the loop counter I. These variables require O(1) space, which is insignificant compared to the memory required for slicing. Combining all factors, the dominant contributor to space complexity is the slicing operation, which can require up to O(n) space for the newly created sublists. As a result, the overall space complexity of the bad sensor function is O(n). This makes the function efficient in terms of memory usage, as it scales linearly with the size of the input data. The space analysis also highlights how the slicing operation, while necessary for the solution, contributes to the memory overhead. When comparing the provided solution to a brute force approach, the differences in efficiency become clear. A naive brute force method would involve comparing all possible shifted versions of sensor 1 and sensor 2. This would require nested loops to handle each possible shift, resulting in a time complexity of O(n squared). In contrast, the optimized solution leverages slicing to directly compare only the relevant portions of the lists. This reduces the time complexity to O(n). Furthermore, the optimized solution minimizes unnecessary operations by exiting the loop as soon as a mismatch is found, which improves performance in both the best and average cases. While the slicing operation adds some overhead in terms of memory, the overall efficiency gains in time complexity make this approach significantly better than the brute force alternative. When tackling problems, there are several common mistakes to watch out for. First, overlooking edge cases is a frequent issue. Scenarios like empty inputs, single-element arrays, or maximum constraint values must be tested. Missing these can lead to runtime errors or incorrect outputs, especially near boundary conditions. Another pitfall is relying on inefficient brute force solutions. While brute force can be a helpful starting point, it's important to optimize your approach for problems with stricter constraints. Inefficient solutions often exceed time limits on larger inputs. Off-by-one errors are another common challenge. These occur when you iterate too far or skip critical elements in an array. To avoid this, double-check your loop boundaries carefully. Finally, don't ignore space complexity. While time complexity often takes priority, excessive space usage from unnecessary data structures can lead to memory limit exceeded errors, particularly for large inputs. Balancing both time and space efficiency is key to crafting robust solutions. Now, another important mistake to avoid is not leveraging problem constraints. Constraints like sorted arrays, distinct elements, or fixed ranges are there to guide you towards simpler and more efficient solutions. Ignoring these can lead to overly complicated approaches or missed opportunities for optimization. To navigate common variations in interviews, begin by thoroughly analyzing constraints. Pay attention to hints such as sorted or constant space, as these often point to specific algorithms like binary search or two-pointers. As you solve, aim to optimize iteratively. Start with a brute force solution, identify its bottlenecks, and refine your approach step by step. Communicating your thought process to the interviewer is crucial here. Additionally, focus on recognizing common patterns. Techniques like sliding windows, two-pointers, or prefix sums frequently apply across problems. After coding, make it a habit to discuss edge cases explicitly. This demonstrates thoroughness. Finally, always analyze the time and space complexity of your solution. If it's not optimal, explain what improvements you would make. This level of insight can set you apart in interviews. To deepen your understanding, let's explore related problems and alternative approaches. Classic problems like twosum introduce the use of hash maps for efficient lookups. Threesum builds on this by adding complexity, requiring sorting and the two-pointer technique. Subarray sum equals k leverages prefix sums and hash maps for efficient subarray sum calculations. Another highly relevant problem is longest substring without repeating characters, which demonstrates how sliding window techniques can yield efficient solutions for substring analysis. In terms of alternative approaches, brute force is a straightforward starting point. It's easy to implement but often inefficient for larger datasets, leading to time complexities like O(n squared, or worse. A smarter option is the two-pointer method, which is particularly useful for problems involving sorted arrays or finding pairs in triplets. However, this approach may require pre-processing to sort the input, adding an O(n log n) step. Hash maps are another powerful tool for problems involving sums or frequency counts, offering efficient lookups at the cost of increased space usage. Each approach has trade-offs to consider based on the problem's constraints. Finally, binary search is a highly effective technique for problems involving sorted data or range-based queries. It allows you to reduce the search space logarithmically, making it an optimal choice for scenarios where time complexity is critical. However, this method is only applicable if the problem provides sorted input or if the data can be transformed into a sorted format. Understanding when and how to use binary search can significantly enhance your problem-solving efficiency. By carefully tailoring your approach to suit the problem's constraints and leveraging the right techniques, you can create solutions that are both efficient and elegant. Great job! We've reached the conclusion of our walkthrough for low-quality data detected. Today, we explored the brute force approach, discussed its implementation, and reflected on the importance of starting simple. Remember, each problem is an opportunity to improve your problem-solving skills. Don't forget to like, share, and subscribe for more content like this. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!